Hi, it's Yohei Kawasaki. I'm from Keio University. My research topic is identification and authentication using Blink with smart glasses. First of all, let us give some background information. Smart glasses have become popular in recent years. Some companies are developing smart glasses for various applications. For example, Google Glass is a smart glasses for augmented reality, and Jeans Meme is a smart glasses for health management. The market size of smart glasses is expected to grow after 2021. Assuming that smart glasses will be carried as standalone devices, they will need to be equipped with identification and authentication functions from the point of privacy. There are three main types of personal authentication. The first is knowledge-based authentication, which involves the risk of forgetting or leaking them. The second is position-based authentication, which involves the risk of loss or theft. And the third is biometric authentication. There are two main types of biometrics. One is based on physical characteristics, such as iris and fingerprints, which is unchanged throughout life. And the other is based on behavioral characteristics, such as gait and handwriting, which express habits and tendencies. In this study, Blink is used as a behavioral characteristics for authentication. There has been research on identification and authentication. With head-mounted device, there is research on helmets that exploit individuals' differences in head shape, and research that use acoustic properties of the nose and skull for use in smart glasses. In addition, there have also been studies of identification and authentication that focus on the blink of an eye. There are studies that use cameras to capture blink patterns and use changes in brain waves during blinking. In this study, we aim to develop a system to identify and authenticate individuals by using a blink as a behavioral feature. Assuming the situation in which smart glasses are carried by themselves. Compared to related drugs, we aim to implement the system using a non-contact, compact, and inexpensive sensor. We also aim to develop a system that is hands-free compared to the authentication system for smartphones and PC. Two photoreflectors are attached to the frame of the glasses to measure the skin deformation of both eyes. When I actually blink, I will get the sensor value like this. Next is the hardware implementation. The overall system is shown in the figure on the right. The sensor values are acquired using a photoreflector and sent to the computer via Arduino Uno. This section describes identification and authentication. Identification estimates the class to which the input data belongs and evaluates its accuracy. Authentication determines whether the input data belongs to the person or not. FRR, FAR, EER are used as evaluation indices. FRR is a false rejection rate. The rate the person is recognized as a stranger, while FAR is a false acceptance rate. The rate a stranger is recognized as the person. And EER is the rate when both FAR and FRR are lowered. Next, this section describes the identification method. When the DTW distance is calculated for all classes for a single input dataset, the class with the smallest DTW distance is the correct class. Next, I describe the authentication method. As an example, we consider the authentication of subject A key. First, the DTW distance D between the input data and the subject A key's dataset is calculated. And here we set the threshold theta. If the distance D is less than or equal to theta, the data is considered as a person's data. And if it is greater than theta, the data is considered as not the person's data. Then FRR is a percentage of the data that is considered as a stranger but a person. So it is obtained by dividing false negative by the sum of true positive and false negative. And FAR is the percentage of data that is considered as a person but a stranger. So it is obtained by dividing false positive by the sum of true negative and false positive. Since the threshold is the boundary value, changing the threshold will change FAR and FAR. And there is trade-off between the FRR and FAR. Then the rate at which the FAR and FRR correspond when theta is valid is defined as EER. And this is used for evaluation. Here is the experiment. 7 subjects participated. Subjects rolled the devices and blinked in 2 patterns. Pattern 1 is blink 5 times in a row at any time. Pattern 2 is blink 5 times in a row at a temp of 120 ppm. Each pattern was measured 20 times. The frame rate at which the sensor values were acquired was 70 fps. And tenfold cross-validation was used for evaluate. First, here are the results for identification. The accuracy of pattern 1 was 88.6%, and that of pattern 2 was 97.1%. Next, we show the result of authentication. The EER of pattern 1 was 8.6%, and that of 2 was 6.4%. For discussion, there was difference between pattern 1 result and pattern 2 result. When I checked the raw data of pattern 1, I found that despite the same people, the timing differs. And I think 3 factors contribute for identification and authentication. The first is blink timing. The second is the length of a blink. The third is distance between sensors and skin. Finally, there are some limitations and feature issues. One limitation is that sensor bodies are affected by sunlight, and it is necessary to adjust the location where the sensor bodies are often acquired. And future works are to expand the range of subjects and to improve the robustness of the system. To improve robustness, we are considering intentionally changing the position of the sensor and measuring on a different day. This is a summary. That's all. Thank you.